time, so I think we should just get started with this session. So, Professor Tom, thank you so much for joining us once again. Please, you can share your screen and then we get started.
Okay.
Yes, we can see your screen now.
Yes, I'm hiding the controls so I can see it.
Oh, okay.
Okay, so yes, I'm sorry that this year I can't travel to Lagos and be with you in person. I was there last year, and it was really nice to see everybody in person. So I hope that uh, the next best thing is we can have these presentations and maybe connect on LinkedIn and so you can ask follow-up questions later as they occur to you. Yeah, I just wanted to show you where I am. I'm here at Oregon State University, which is in a small city called Corvallis over on the West Coast, where it is raining right now very, very intensely. We're into our winter time. And my original title for the talk was 6 Challenges for Machine Learning, but then I decided I really wanted to make it 7. And my goal in this talk is to talk about what I see as the important challenges going forward for the field of machine learning, but also to tie it to some of our history. So the very first machine learning workshop was in 1980, and it was held at Carnegie Mellon University, and organized by 3 young professors at that time: Jaime Carbonell, Tom Mitchell, and Richard Michalski. And of these, Richard passed away a few years ago. Jaime died earlier this year. So Tom Mitchell is now the only one still living and actually still active at Carnegie Mellon. There were only 30 people at that meeting. And so we just met in a classroom. And I think if you went there, you would not recognize any of the topics that were discussed as machine learning or data science. The focus was on exact learning. We had, and the idea was that there was a right answer, a single right answer, and the goal was to get the machine learning algorithm to find that right answer. So we call that exact learning. And so it was supervised learning with noise-free labels, no probabilities, no uncertainty. And in fact, in some cases, as we'll see, it was really just about lossless compression. So anyway, the plan for my talk is to, with that as a starting point, see a bit about how the field of machine learning has changed over 40 years, and in particular to talk about these 7 challenges that I see as critical to the field moving forward. So the first challenge is generalization. Now, of course, we normally test how well our algorithms generalize by starting with our training data and then having a separate validation and a separate test data set and asking, well, after training on the training data, do we have high accuracy on the test data? And what we find is that in general, that we can do very well by that measure, right? But what we're seeing, this actually, if we go back to that first machine learning workshop, the most important paper, we didn't have a best paper award in such days, but the most important paper was from a young guy named Ross Quinlan, who's now retired after having taught at New South Wales Institute of Technology for many years. And Ross introduced something called the Iterative Dichotomizer 3, or ID3, which was a decision tree algorithm. And his goal was to compress chess endgame tables into simple decision rules. So Ken Thompson, who was the originator of the Unix operating system, had another project which was to do what was called reverse enumeration of chess games. So you can start with the final, checkmate in a chess game and play it backwards in all possible ways. And particular chess end games like this one here, we see a black king against a white king and a white knight. So this is, or white rook, excuse me. So this is king and rook versus king is one, a classic end game. And Thompson had reverse engineered these so that he had these huge tables of board positions, and then the outcome of the game. Was this a winning position or not? And if it was a win or loss, then how many moves until the win? So this position would be labeled as something like win in 10 moves. And based on this data, which was a complete set of all possible training examples, right, for this end game, ID3 would compress that giant table down into a decision tree, which was printed out like this, because we didn't have graphical user interfaces in those days either. And Ross's idea was that chess players could memorize these decision trees as a set of rules and then play perfect endgame chess. So there was no generalization, it was noise-free, but interpretability of the learned knowledge was very important. Well, fast forward to today, and we see that generalization is the key. We obviously want to be able to generalize beyond our training data. And if our data is so-called IID, that is independent and identically distributed, so the probability distribution that's producing the data is stationary, unchanging, then we have beautiful theory that tells us that if we do well on a sufficiently large data set for a sufficiently simple rule class or concept class, then we have a very high probability that we'll do well on new data. But we'd really like to generalize across domains. For one thing, anyone who's done real applications knows that the data are not IID, that at runtime, we're going to see data where the distribution has changed in some way. And so do we have any ideas about how to proceed? Well, I wanted to mention two of them. The first is called causal transportability. So many people in machine learning are excited about this new theory of causality that has been developed by Udaya Pearl over the last 20 years. So it's maybe not brand new, but new. And it's based on directed acyclic graphs, or DAGs, defined over a set of variables. So for instance, in this case, imagine that we're in a medical situation and we want to fit a model, say, at one hospital and then apply it at other hospitals, or maybe train a model in one country and apply it in different countries. And so let's consider this particular simple causal model that says if a person has lung cancer, that could cause them to also have chest pain. If they are taking aspirin, that might reduce the probability of chest pain. And it could be that smoking might cause both the cancer and might cause them to take some aspirin. So these are our four variables: cancer, chest pain, taking aspirin. And this is a hidden variable. That's why it's a white circle here, which is whether or not they are a smoker. And so what is this S variable? Well, this S variable is something that's introduced by Elias Barenboim, who is one of Pearl's students, and now is a professor at Columbia University in New York. And Elias calls this a selection variable. And the idea is that you are going to mark this aspirin node as something that might change when we move from one hospital or one country to another. In some hospitals, if a person comes in complaining of chest pain, they might give them aspirin immediately. In others, they might not. So it might change. So our goal is to create a predictive model that will transport from one hospital to another without retraining. We want it to be based only on the things that are invariant, that are causally underlying the phenomenon, and not the things that might be changing. So in particular, if we can create a predictive model that does not depend on this S variable, then, and if the causal model is correct, then we'll be able to generalize to new hospitals. And this work was refined by some work coming out of Suchi Saria's lab at Johns Hopkins by a student of hers, Subaswamy, 2 years ago. They developed this graph surgery technique, and their approach was that you can generate many different machine learning models that make the cancer variable independent of the selection variable S. And we can generate those and evaluate each of them on validation data and keep the most accurate model on the training data. And this is, again, guaranteed to transport across hospitals, provided that the causal diagram is correct. But I think beyond just the importance of causality, and the idea of causality is that these causal processes are invariant. Uh, I like to say, it's causal modeling that lets us understand what might be happening inside a black hole, even though we can never visit one, or at least never visit one and survive. But beyond that, it really encourages us to think ahead about possible changes that could occur at deployment time and to prepare in advance for those changes. And I think that's something that has traditionally been missing from our machine learning kind of development mindset, which is we haven't been thinking ahead to what might change and making sure we can handle it. Okay, the second idea that's kind of related is called domain adversarial training. And the idea of domain adversarial training is to imagine we have data points from 2 or more domains. So again, we could imagine that domain 1 is a hospital 1 and domain 2 is a second hospital. But only our data for hospital 1 is labeled. So we have our labeled pairs of data here with inputs xi and the output class label yi. But for domain D2, we have only unlabeled data. And the idea for domain adversarial training is that we're going to train a combined neural network model for data points that belong to hospital 1, predict the correct label. And for all points, predict whether that data point xi came from D1 or from D2. And what we want to do is find weights that give accurate predictions for the label, but only predict at the level of chance, 50-50, for predicting which domain the data point came from. The idea is to find a predictive model that works well, but that is not cannot detect any difference between domain D1 and D2, so it's invariant to the choice of the domain. I think a network picture is clearer, and this is work by Ganin et al., published in the Journal of Machine Learning Research now 4 years ago. But the idea is to have a neural network that is has what we call 2 heads. So it has this input here, which is, I guess, its tail, and so the inputs go through some series of layers, and they come to a hidden layer that is the layer of features. And then we have a blue network and a red network, both that read those same features. The blue network tries to predict the class label, and the red network tries to predict the domain label. So for data points that belong to domain 1, we label them domain 1. And for data points that come from domain 2, we label them as domain 2. And so for domain 1 data points, we push them through here, and they go out the blue side because we have their class label, and we can calculate our loss, and we can use backpropagation to modify the weights in this network. But for data points from both domains can go through the network and out on the red subnetwork, where they make a prediction for a domain, and we calculate the gradient direction that would most improve their accuracy at predicting the domain. And then we flip it, and we actually train the weights to destroy that accuracy. So it's a bit like adversarial, generative adversarial networks, if you're familiar with those. We want this red network to do no better than random guessing on the task. If we succeed, that means that there is no features in here, and therefore no gradient we can compute that allows the red layer to correctly predict the domain. So they showed in that paper, they called it DAN, Domain Adversarial Neural Network, that it could do much better, not beautifully, but much better than training on the source domain only. So consider this pair here. The source domain was MNIST, handwritten digits, and the target domain was a transformed version of MNIST where things have been colored and the background has been artificially modified. Okay, and so the idea was to train a classifier in the source domain, but then have it work well in the target domain, given only unlabeled target data. And so the blue bar here is how accurately the system could work if it was trained only on the source and then just tested on the target. And it gets about 50% of the images right. But if they use this domain adversarial training, it gets something like 78% of the instances correct. So that is much better. Now, of course, if we had labeled training data for the target, we'd be able to get up to about 96% correct. So there's still a big gap. But domain adversarial training has reduced that gap by more than 50%. Right? And you see similar improvements in all these other cases. Roughly a 50% reduction in the gap between the training only on the source domain and cheating if you had labeled data for the target. So this is a way of getting at domain invariance in the absence of a causal model. One weakness of domain adversarial training, when you first see it, you say, oh, it's so cool, that solves the problem. But it turns out that the method assumes that the class label distributions are not changing between the domains. And that might not be true, for instance, in our medical example, the fraction of people having lung cancer at one city might be different than at another. So the class label distributions could be changing. Also, the method can be unstable. And that's true for a lot of these adversarial training techniques. The optimization problem is hard to solve. And people find it works best if you have at least some labeled data in the target domain to help with choosing learning rates and other hyperparameters. Okay, challenge number 2, which is feature engineering. Now, of course, when Ross Quinlan was building his chess endgame system, he carefully designed interpretable features. So I won't scroll back to it, but if you look at the features that were in his decision trees, they were things like distance from the white king to the nearest corner, distance between the two kings, and things like this. So very much relocatable patterns, right, that were position independent. And of course, feature engineering is very important for success in any machine learning, data science type application. But I would say there's one area in our practice that we should improve, and that is that we should make sure that we capture the definitions of our features as metadata. So there's a professor at the University of Toronto, Mark Fox, who likes to say numbers should never travel alone across the internet, meaning they should always come with a metadata that describes them. And that metadata definition could be in a mathematical notation. So one of Mark's examples is the definition of student-teacher ratio. He was doing a bunch of data and analytics for the Toronto School District, and they were interested in the student-teacher ratio. And it changed suddenly one year, and he was trying to figure out why. It turned out that what had changed was the definition of Toronto had changed so that it now included some schools that it hadn't included before, and that changed the statistics. But he didn't have a definition of the feature, he just had the name of it. And so he said if he had had these numerical definitions like this, right, it says that the student-teacher ratio is the cardinality of the set of all students that are registered in some school at some time in the school district, divided by the total full-time equivalent percentage of the teachers teaching in that school at that time. So earlier today, Guillaume and I presented BigML, and he briefly mentioned that BigML has this language called flatline that lets you define features like this. And of course, you can also write feature definitions in SQL, and you can write them in Python and so on. But the key thing I just want to make is we should be collecting metadata for all of our features so that we have complete understanding of where the features come from. Now, some people would say, well, doesn't deep learning automate feature engineering? And I think the answer is yes and no. On the other hand, on the one hand, definitely not, that even deep learning applications require careful data preparation. So if you look at a typical computer vision pipeline, there's a huge amount of stuff happening up front about normalizing the images, doing contrast enhancement, maybe histogram equalization, all kinds of things, camera calibration if possible. But there is a sense in which deep learning does do some automated feature engineering. We know that on the famous ImageNet benchmark problem, there was an annual competition that started in 2010, and performance in 2010 and 2011 was based on manually designed features, things called the SIFT, which is scale independent feature transform, and the histogram of gradients or HOG feature. And we computed those over the whole image and then combined them with support vector machines or random forests to get our final classifiers. But starting in 2012, of course, with Alex Krzyzewski's famous paper coming out of Toronto, he showed that deep learning could produce much better results, and it did it by learning its own features in some sense. And so this is what Rich Sutton calls the bitter lesson, the lesson that often we can learn better features. From a machine learning point of view, it's an exciting lesson that we can learn better features than we can code by hand. But keep in mind that to learn features, you need a lot more data. And that despite this learned features, there is also a huge amount of work encoding knowledge into the neural network architecture of a convolutional neural network. So yes and no is the answer. Okay, the third challenge, and the one that maybe is is the least clear, so let me see if I can make this clear, is about deep representations. So one of the things about deep learning, right, is that it is learning some sort of intermediate representation. I had this picture here, right, where we have this intermediate representation that we call the features, F. And so that is sort of the focus of our learning. We even have a conference called the International Conference on Learning Representations. But I think we're discovering that these deep learning systems are not necessarily learning what we want them to. They may be failing to learn what we want them to and learning something else instead. And let me present 3 pieces of evidence that we don't really understand what the deep networks are learning. The first piece of evidence is about adversarial examples. And I imagine many of you have seen this example before. But it was shown fairly early on that if you take an image, for instance, of a panda, and the neural network is moderately confident about, say 58% confident, that you could add a special perturbation vector that to our eyes looks like random noise and get an image that looks very slightly changed, maybe a little fuzzier, but which the neural network will classify as a gibbon with very high confidence. And this is a so-called adversarial example, this gibbon, this image that looks to us like a panda, but looks to the neural network like a gibbon. And the feeling was, wow, an attacker could lead our system to make big mistakes. So the field has been trying to figure out what's going on with this, right? I think these were discovered in 2016, maybe. So Alex Madry at MIT has put forward the following hypothesis. He believes that the networks are learning valid regularities that are not visible to human eyes. And what the adversarial examples are doing is changing those regularities. So when the computer sees this, it doesn't see what we're seeing. It sees something else that tells it it's a panda. And this change here tells it now it's a gibbon. This is published in a paper. The first author is Ilias. I'll have all my references at the back end, and the slides are available. So they've done a bunch of experiments to try to do this. I mean, unfortunately, the evidence is indirect because we don't see, if their hypothesis is true, then we don't see the stuff that the computer is seeing. But it feels a little bit risky, like phlogiston. It may be that this is not the correct explanation. But in any case, here's a piece of evidence that we don't know what's going on. Another piece of evidence comes from the area of what are called deep generative models. So these are models that try to learn a probability distribution, P of X, as shown here, that assigns high probability to data points that come from our training data. And we wanted to assign low probability to data points that come from other distributions. We'd like to use this to do what's called out of distribution detection, or outlier detection, or anomaly detection. And so if you train it on ImageNet training data, you get this histogram. It's kind of hard to see here, the black histogram. And these are the log likelihoods assigned to the ImageNet training data. And sure enough, it assigns similar log likelihoods to the ImageNet test data. So whatever it has learned it reliably so that it generalizes from training to test. But now what we would expect, what we would hope or expect is that if we gave it data from, say, CFAR 10 or CFAR 100, which are smaller benchmark data sets, or from the Street View house numbers data set from Google, that it would assign much lower probability to those images because they come from a different data set. But instead, shockingly, it assigns higher likelihood to these, especially the house numbers. It thinks they are much more, have much more higher probability than the images that from ImageNet, which is just crazy. And so people have been scratching their heads about this, and various hypotheses have been put forward. The one I like was just published a month ago by Ziyu Wang and colleagues in an archive paper. And they basically show or present two hypotheses. One is that these models are basically learning local correlation structure in the images rather than higher level, more abstract features. In a sense, the probability models are trying to judge the probability that the image is a natural image. And sure enough, the ImageNet images are natural images, but so are the CFAR images. And so are the Street View house number images. And in some sense, the correlations exhibited, especially by the house numbers, these images have been are somewhat blurry and smoothed compared to ImageNet. And so they may look more natural than ImageNet in terms of these local correlations. A third piece of evidence is a kind of, it's not an example of a failure, but an example of a surprising success. So one of the problems that I have been working on for the last several years is the problem of what's called open category detection. So the question is, normally we train a neural network such as this convolutional neural network or any supervised classifier. We train it on, say, K classes, in this case, 10 classes, which are the 10 digits. And what we're implicitly telling the learning algorithm is that there are only 10 classes in the universe. And your job as a classifier is to partition the image space, in this case, the X space, by laying down decision boundaries that divide X up into 10 regions that correspond to the 10 classes. And any new input that falls into one of those regions will just be classified according to the corresponding class. But what happens if we're in an open world? For example, maybe you've trained your self-driving car and you've trained it in Europe. And so it knows about deer and it knows about bicycles and maybe it knows about, other cars or something. And now you take it to Australia. What does it do the first time it encounters a kangaroo? It should detect that this kangaroo is something new that it hasn't seen before, and it should be very cautious around it because it doesn't know, is a kangaroo dangerous or is it okay? How should my self-driving car behave? So I always just made up this example, but it turned out to be real. That when I believe it was BMW, when they took their car that had been developed in Europe and tested it in Australia, it was confused by kangaroos. I mean, who knows what it would have done if it had encountered a giraffe or a zebra or something. So what's my surprise here? Well, if we train a convolutional network in the usual way, and if you think about it from a discriminative training point of view, from an information theoretic point of view, it really, if there are 10 classes, it only needs to extract 4 bits of information. Actually, 4 bits would be sufficient for 16 classes, right? That's the minimum encoding of the 16 classes. And that's all it needs to extract to make that a 10-way decision. But for one reason or another, for reasons we don't fully understand, convolutional neural networks actually don't throw away, they don't learn the minimal information. They actually retain some additional information. And it turns out that we can ask, is there enough information in this penultimate layer Z, which is the feature layer, for us to detect new classes? So for instance, if we train a network like this on the CFAR 100 data set, where we train on 80 classes and then test on all 100, and we want it to detect that data from the 20 novel classes as novel, we can use a simple thing like the uncertainty over the 10 known classes to calculate a binary decision. Is it a new class or an existing class? And get an area under the ROC curve for that binary decision of 0.724, which is much bigger than 0.5, which would be random guessing, which we would have expected. So the learned representation, despite the fact that we trained it in a closed world, actually has retained some additional information that's enough for it to do some open category detection. I mean, we'd really like this to be 0.99, obviously. So it's not a very good open category detector, but it's much better than I expected. Well, I think we need better ways to somehow constrain the learned representations. And so an important open challenge for machine learning these days is to come up with such techniques. And one of them is to introduce self-supervised auxiliary tasks. So there was a paper 2 years ago by Golan and Elyaniv in which they created a two-headed neural network again. So it takes as input, the inputs go here, and this is my feature representation. And then one of the heads has to predict the class label. In this case, what digit it is. And so it might say, well, the probability that this is a 3 is 0.89. But the other output needs to predict for an auxiliary task, and the auxiliary task is rotation. So given this 3, we can rotate it by 45 degrees or 90 or 270, or we can rotate it by various amounts. And we can label those images with the amount of the rotation. And even on test images, we can apply this. And so we can ask the network to predict what was the rotation. And hopefully it would say, well, the rotation for this one was 45 degrees. And maybe it assigns a probability of 0.95, something like that. Now, Golan and Elyaniv did this because they wanted to have to detect anomalies or out of distribution queries. And what they found was that if this classifier, given a new query, we can ask this head to predict the amount of rotation. And if it can't give us a good answer, if it can't do that, correctly predict the rotation, then we won't trust its class prediction either. So that was their idea, that we could use these auxiliary tasks we're constraining the learned representation by giving auxiliary tasks. And you can imagine giving dozens of auxiliary tasks. So people have looked at taking an image that was a color image, making it a black and white image, and then asking the network to colorize it to restore the original colors as an auxiliary task. And the thought is that to do that task, you have to understand the meaning of the image, at least to some extent. And so on and so forth. Well, another tool we have is this adversarial strategy, right? So consider this data down here. We have 4 classes of objects: spoon, sink, mug, and pen. And we have each of those rendered in 4 different styles, we'll call them. So we have real world images, we have product catalog type images, we have clip art images, and we have artistic renderings. And what we want the network to do is to correctly predict the class label while doing no better than random guessing on the style. And the goal is to make the network be invariant to style, and hopefully it will generalize better. So this was introduced by Edwards and Storkey and was really inspired by the domain adversarial training idea. They were concerned with creating networks that don't use illegal or regulated information. So for example, if we were doing trying to assess creditworthiness, credit scores for people, we are not allowed to use sex or race or age in such a rating. So they had the system try to predict the sex or the race or the age as an auxiliary task, and then in the same as with the domain adversarial training, ensure that this representation can only do as well as random guessing on the sex of the person. And that means that even if there is information about sex, either explicitly or implicitly in the inputs, it's not available to be used to predict the output. So this is another tool. Of course, I skipped one thing, which is the first method is data set augmentation. We can just take each of the inputs and apply various transformations to it: color corrections, adversarial perturbations, image corruptions, and of course, Madri's group at MIT introduced adversarial training as a general strategy. So we can see we have two different ways to try to make the hidden representation be invariant to these kinds of changes. One is augmentation, and the other is adversarial constraint. Okay, so there are a couple of tools that we have. I would say 3 tools that I just introduced for trying to improve what's being learned in these latent representations. But I think this is the central question right now in deep learning, in my opinion, is this question of how to constrain the learned representation. Okay, well, challenge 4 is explanation and interpretability. Again, if we think back to 1980, Quinlan wanted interpretability because he expected people to memorize the learned decision tree. But today, I think our biggest need for interpretability or explanation in machine learning is that we as machine learning engineers need to understand whether the model is getting the right answers, and if it is it getting them for the right reasons? Unfortunately, our highest performing models, things like random forests, boosted trees, and deep neural networks, are not interpretable by themselves. They're black boxes, essentially. So of course, interpretability and explanation are very hot topics right now in machine learning research. And I'm not going to review all the things that are happening there, but I do want to get one message across, which is that we shouldn't expect that there is a single explanation technique or a single interpretability technique that will solve our problems. Instead, I think the explanation needs to be customized to the user and to the task they're trying to perform. So let's look at a couple of cases. Imagine we have a machine learning engineer like me, and I'm trying to build a predictive model like a classifier. But my task is I want to find errors in the learned classifier and maybe caused by holes in the data. So I want to get a sense of what parts of the input space have insufficient data that's causing the uncertainty of the classifier to be large. And in that case, maybe I can go collect more data for those cases. Whereas if we compare that with an end user that's being given a recommendation, say a recommendation for a TV show to watch, they need to decide whether to follow that recommendation. So they want to know, why did you recommend this? And the system can say, well, you liked shows X, Y, and Z. This one is similar. People that like those, they also like this one. So maybe you'll like this one too. Another use case is acceptance testing. And this is the one we've been studying at Oregon State. Suppose that I purchase a trained model from some model supplier, and that might be a predictive model or a reinforcement learning model. And I need to decide, I want to test it to decide whether to pay for it. You know, is it, when it's delivered to me, is it sufficiently accurate? Is it working correctly? And so in that case, it's more of a kind of software testing setup. I want to understand whether I've covered, have test cases that cover the entire input space, and whether the model is looking at the right relevant attributes. So we might use various visualization and contrastive explanation techniques. The fifth challenge is uncertainty quantification. So again, if we go back to 1980, in the first machine learning workshop, no one even mentioned probability. Uncertainty was just not relevant at all. But today we see that giving a calibrated uncertainty estimate is very important for our machine learning models, particularly because they are usually just a subcomponent of a much larger system. And that larger system needs to not only get the classifier decision, but also its confidence score. Well, what do I mean by calibrated probability? Well, when a classifier says this input X belongs to class C with probability 0.94, we say that that statement is well calibrated if 94% of the time it's actually true. So if we collect up all the X's where the classifier says class C probability 0.94, then 94% of the time, the class C should be the right answer. So we can measure the calibrated probabilities using a separate labeled calibration set, which we can actually reuse our validation set more or less for this purpose. Some learning methods, some fitted models are always well calibrated. So decision tree models are very slightly biased, but generally are very well calibrated. Random forests are also very well calibrated. But other methods like boosted trees, support vector machines, and also many deep neural networks, particularly ones that use the residual block like ResNets, these seem to lose calibration as they become more accurate, as the iterations proceed. Well, how can we measure calibration? An important early paper in the machine learning literature was by Zadrozny and Elkin back in 2002, and they introduced this reliability diagram. I don't think it was original with them, but they were the ones who imported it into machine learning because calibration was originally studied by people in weather forecasting, because when they say there's a 30% chance of rain, they should be right 30% of the time, right? It should rain 30% of the time. So anyway, in a reliability diagram along the horizontal axis here, is the score that's coming out of your fitted model. In this case, we're using a naive Bayes model, so that's why it says NB. That's the probability from a naive Bayes model. What we're going to do is bin those probabilities into bins, 10 bins, 0 to 0.1, 0.1 to 0.2, and so on. And then in each bin, we'll look at the validation points that are in that bin. In this case, there were 8,941 validation points in this bin. And about, what would you guess that says? 0.03 of them belong to class 1. That's what we would expect, because if things are perfectly calibrated, then these stars should lie on this diagonal line. But let's come out here and look at these data points that are in this bin between 0.8 and 0.9. So their average probability of these 672 points, the model is predicting 0.85. So it thinks that it's 85% confident, but in fact, it should be about 51% confident. So the fact that all of these points lie very far below this diagonal line is evidence of overconfidence of the classifier, wildly overconfident in this case. And this has been noted for naive Bayes, is that often because of its naiveness, if it pretends the feature values are uncorrelated with each other, and when in fact they are correlated, then that causes this overconfidence. Well, what can we do about it? The sort of interesting, cool discovery is that it's quite easy to calibrate these classifiers. You can often fit just a simple logistic regression, just a sigmoidal curve to the scores. So this is for a different data set, and this is the support vector machine score, which is basically its margin. And these are the empirical probabilities of the bins. And you can see that it obeys more or less a sigmoidal shape to it. So what you can do is you don't actually fit the function to the diagram. You fit the function to the individual data points, because for each one, you know whether it was belonged to class 1 or class 0. But you fit a logistic regression model that has only one input feature. That one input feature is the output of the support vector machine, its score here. And then you map that onto well-calibrated probabilities. And similar techniques can calibrate naive Bayes and deep nets and boosted trees. In fact, if we go back to the naive Bayes diagram here, we'll see that the sigmoidal curve could fit this pretty well also. So, but it doesn't always work. So here's a bit of unpublished research that I've been doing with my colleague, Thierry Wagstaff. And we're looking at so-called local calibration techniques. So what I've described here so far, these are global calibration techniques. I fit a single function for the entire space, and then I use it to map the scores. But if I do that here, suppose that my problem is to separate the red triangles from the blue circles, and I'm using a linear support vector machine. So the false color in the background here shows the decision probability after calibrating the support vector machine probabilities. However, we can see that a linear support vector machine is not a terribly good model here because the data are not linearly separable. A true separating boundary would have to curl around somehow. And in particular, if we look at one of the probability bins, for instance, the bin from 0.5 to 0.6, that would cover the points that are in this region here that I've shown. And we can see that there are areas here that are basically all red and areas that are all blue, and maybe some areas that are mixed. So what we do is to apply a sort of special kind of clustering approach where we cluster together points that are close to each other in the input space and also close to each other in terms of the probability score that was assigned by the classifier. And then we calibrate each cluster by fitting a constant function. One could also maybe fit a sigmoidal function, but we fit a constant function. And we find that this improves our calibration and also makes the classifier more accurate. In this case, it's able to overcome the problem that the classifier was a linear classifier. But I think the lesson here is that if you're calibrating a classifier, it's probably wise to do it separately for each customer segment or each local group rather than trying to do it globally. Okay, well, challenge number 6 is about runtime monitoring. I just want to emphasize the importance of this. I think that whenever we deploy a machine learned model, we should deploy with it a monitoring system, for instance, an anomaly detector. And I've mentioned, of course, that predictive models are only guaranteed to be accurate if the runtime queries are drawn from the same distribution as the training data. And we need to detect when there is a departure. And a particularly, salient version of this is the open category problem, where the runtime data may involve new classes of objects, new types of items for a recommender system, new diseases for a medical system, new fraudulent attacks for a fraud detection system. Well, how can we monitor? Well, one thing we can do is outlier detection, and another thing we can do is what's called change detection. So outlier detection, there's a subfield of machine learning called anomaly detection, and I'm giving a whole session on it tomorrow. But the state of things back in the early 2000s or mid 2000s was that there were a lot of papers published, but they were not very well evaluated. So my student Andrew Emmett did a big benchmarking study. We chose 19 different data sets from the Irvine repository, and we manipulated them in various ways to get several thousand test data sets. And then we compared 8 different anomaly detection algorithms drawn from these 4 different general categories of anomaly detection methods. Ones that fit probability densities, ones that use nearest neighbor distances, and ones that project down into lower dimensional spaces and then do something like the above. And what we found was that we measured two criteria. One was the area under the ROC curve for the problem of detecting whether something is anomalous or not, converted to a log odds scale, or the lift, which is basically the average precision, again, transformed to a log scale. What we found is that the isolation forest method was the top performer. And isolation forest was mentioned earlier today in the Big ML section, basically builds randomized trees, and I'll go through it tomorrow. Then there was a 5-way tie for second place. And then the methods that performed the worst were the support vector data description and the one-class support vector machine, which actually many people believe is a very good algorithm, but it hasn't performed well in our experiments. So we use this to do open category detection by using the following setup, right? We have our training examples. From our training examples, we can fit both an anomaly detector and the classifier. And so then given an input xq, q for query, we first calculate its anomaly score, a of xq. And if that's greater than some threshold tau, then we reject the data point, basically raise an exception and say, I've got a suspicious data point. It's far away from my training data. I refuse to classify it. But if it's less than tau, then we go ahead and classify it with our classifier. So we're basically building an anomaly detector as a shield around our classifier to protect it from strange data. And we had a paper at ICML 2018 giving a theory behind this about how we might be able to guarantee to find, say, 99% of all of the anomalies, all of these open category queries. Another thing you can do is change detection. This is more general, but given that we have our data arriving in some time order, we can ask, is the distribution changing over time? And so if we take say the most recent 200 data points and divide them into two sets, set A and set B, we can then ask, is set A come from a distribution than set B? And this is known as a two-sample test. Is PA different from PB? And so you can, if you look online, there's some interesting work that was originated with Arthur Gretton, who's I think at the Gatsby Institute, and Arthur developed this kernel two-sample test that's very nice. Another strategy, which is, I don't know if it has a fancy name, I call it the old versus new classifier. It's just, let's try to train a classifier. We'll label all these guys as being old and all these guys as being new. And then we ask, can we train a classifier that can do better than random guessing at telling the old points apart from the new points? If we can, then that indicates that there's a change in the distribution. And there are ways of accumulating change scores over time that's called the Q-sum method, that's based on something called the sequential likelihood ratio test. So there's a whole literature on change detection out there. But I don't see a lot of this being used in deployed machine learning systems, but it should be. Okay, well, the very last challenge I want to mention is evaluation. And I just want to make one point here, which is that application-specific metrics are essential. The standard metrics that you see, things like F1 and area under the ROC curve, were developed really by machine learning researchers to compare machine learning algorithms in an application-independent way. But most applications require different metrics. So for example, if we were working on financial fraud, suppose I have 5 fraud analysts that work at my company, and each analyst can only look at 10 fraud cases per day. So I have a total capacity that I can look at 50 fraud cases per day. So my metric has got to be something like, what is the total value to the company of the top 50 alarms each day? So we can think of each anomaly alarm as combining both how weird a particular transaction looks like, and also how valuable that transaction is. If it's a fraud that's worth $10,000, I'm much more concerned than if it was worth $1, right? And so this is a metric that's something like expected value at 50, which is nothing that any machine learning system calculates in their default settings. And there are many more examples I could give. Open category detection, we might want to detect 99% of all the open category queries. In a self-driving car, we might want to detect 99.999% of all dangerous obstacles. So our metric would be something like precision at 99.999% recall. But there are some domains like cancer screening where different patients might have different trade-off points for false alarms and missed alarms. And in that case, the area under the ROC curve actually is a good metric. Okay, well, let me just wrap this up and summarize and say that I think these are 7 frontier problems that we need to deal with in machine learning and machine learning applications. We need to be able to generalize beyond our training data and beyond the training distribution. And so a couple of ideas there are causal transportability and domain adversarial training. We still need to do feature engineering despite what deep learning can do for us. And if we're doing that, we should capture metadata of the feature definitions and make sure we have that with the data. I spent a lot of time claiming that our deep networks are not learning what we want them to do, and they're learning things we don't want them to learn. We need better methods for controlling the content of learned representations. I talked briefly about explanation and the challenge there, and that it really is user task specific. I talked about probability calibration that lets us do good uncertainty quantification. And I think that's an exciting recent discovery in the field. And then runtime monitoring, briefly talked about anomaly detection and change detection. And finally, the importance of application-specific metrics. And with that, I will stop and answer questions, but I have all my bibliography here for you to look at. Thank you very much.
Hello, thank you. That was an interesting session. I saw a couple of okay, I can see a lot of thank you messages already. Okay, let's check the chat window if people have more questions. For everyone, definitely the video and the slides for the session will be in your bootcamp package. Is definitely something to look back at. You saw all the places where we I think my favorite part was where is deep learning all the things we think it's learning. So I like the fact that the question has been raised, and if you have more questions about it, let me check the chat window so that while we wait for the next speaker, we can answer those questions. Okay, Lekon, are you back online?
Oh yes, I am. I am, Mura. I mean, that was a fantastic session. Thank you so much, Professor. We really appreciate your time.
And it was clear. I like the fact that it was clear. You could
Yeah,
follow the thought process,
exactly,
and that's interesting.
exactly. I
So,
mean,
team, I can see a lot of thank you messages. Do you have questions? Do you have questions related to the presentation? I understand that we understand the fact that some people are quite new to many of the concepts here. Don't be afraid. It's part of why you're at the boot camp.
Right.
It's to be aware that this exists. Yes, we have we have starters. It's to be aware of all the things that exist for you to learn, to read more about, to learn more about, to understand that thought process. So don't be afraid. You can definitely watch the video, read through the slides again. Okay.
So I think, I mean, I think a lot of the things I discussed here are really where, say, research is right now. You can see I'm pretty much up to the moment on some of these. And so these are the kinds of topics that if you were thinking about graduate school, these are places where you might find your master's topic or a PhD dissertation topic. So, but you can see that I have a bias toward research questions that are relevant to industry practice. So particularly the feature engineering, runtime
Exactly.
monitoring, and uncertainty quantification, I think are things that we need to be deploying now, and they're ready to be deployed. So, well, thank you very much for your attention and your enthusiasm. And I will see those of you tomorrow who want to hear more about anomaly detection. And
exactly,
we'll do a deeper dive on that. But
exactly.
I will say goodbye for now
All
and
right,
talk to you all later.
all right. Bye bye. Thank you so much.
All right.
Okay, bye bye.
Bye bye.